Now we're going to talk about aldehydes and ketones. Remember, last week we had a conversation about alcohols, basically the organic compounds that, among other things, have the OH group, right? Now, aldehydes and ketones have also a common functional group that we call carbonyl group. An example of a ketone that people use in the households is an acetone, which has multiple other names, but for example it is used as the nail polish remover. So both ketones and aldehydes, so-called carbonyl group. So you can see that this carbonyl group is a carbon, the black circle, and an oxygen, the red circle. And the carbon is attached to other groups of atoms. Okay? And the versions of that can be the following. It can be this. Okay? Another carbon and a hydrogen. In this case, it's an aldehyde. Or, alternatively, we can have a carbon and another carbon. In this case, it is ketone. So you can see that oxygen carries slightly negative charge and carbon carries slightly positive charge. It's very easy to explain because you may remember that oxygen is much more electronegative than carbon. Okay, in addition to that, we were mentioning briefly before the concept of a lone pair of electrons. So oxygen does have a lone pair of electrons, which significantly increases its reaction ability. Okay? Now, when you look at this depiction of the carbonyl group on the right, you can see that it's significantly polar. There's a lot of negative charge on the oxygen and a decent amount of positive charge on the carbon, and they do not compensate each other. In other words, the presence of carbonyl group makes a molecule, often an organic molecule, makes it polar. Now, as we just discussed before, the atoms that carbon in the carbonyl group is attached to determine whether it is an aldehyde or ketone. So, if we are looking at an aldehyde, we are essentially referring to the situation when a carbon is attached to another carbon and a hydrogen. Okay? In case of ketone, this central carbonyl carbon is attached to two other carbons. Does that make sense to you? The whole idea here. So this is what, so in other words, if you think about this, in aldehyde compounds, the carbonyl group is at the very end of a chain. Am I making sense? In the ketone, the carbonyl group is somewhere in the middle of a chain. So for collapsed structural formulas, this is how we refer to an aldehyde group often, just CHO at the end. Okay? So in the middle, the keto group is often referred to as CO. So for instance, you can see propylaldehyde can be written the following way when the carbonyl group at the end of the carbon is compacted to CHO. And of course, you can use the line angle formulas. So remember that each end of the line, or an angle, represents carbon and hydrogens you can figure out, remembering if they're that the carbon can only produce 4 bonds total. So far so good. Same story, this is the acetone or propylketone. You can shorten this carbonyl group in the center by writing CO. Any questions on writing, depicting that kind of things? No. Okay. So, how do we name? So let's say we have an alkane. I'm going to give an example. Let me just change it. So let's talk about the IUPAC, the proper nomenclature. So let's say we have methane, right? What do we change E for? We change it to AL. Methanol. Does that make sense? So, the formula for methane is CH4. Everybody agrees on that? Now, since methanol has the same number of carbons, we have a carbon, oxygen, there are 2 more bonds, right? There can be only 1 carbon in methanol, so we fill these bonds with hydrogens. Does that make sense? Couple more examples. I'm going to just do propane. Okay? We change last E to AL. Propanol. The formula, how many carbons are in propane? 3. So you change it to this. Does that make sense? This is the proper naming of aldehydes. Now, there are common names for the first 4. Okay? Form aldehyde, acid, aldehyde, propionaldehyde, and butyraldehyde. So far, we clear, everybody? Okay. So you need to know the first 4 common names because they are often used in textbooks and exams and board exams, whatever. They are often used instead of proper IUPAC nomenclature. Okay? So these are some examples. For instance, as we mentioned before, if you have 1 carbon, it's going to be methanol or formaldehyde. If it has 2 carbons, it is ethanol or acid aldehyde. If it's 3 carbons, propanol or propione aldehyde. And if it's 4, butanol or butyraldehyde. Questions about that part? Anyone? All good? That's fairly straightforward, I think. Now, with the ketones, we also replace the terminal E in the name of an alkane, but we replace it with O-N-E. So, for instance, if you have 3 carbons in an alkane, we call it propane. Does that make sense? So, propanone. We basically replace in propane propanone. And by analogy, we do, butanone. Now, I want to highlight something that is different between ketones and aldehydes. So let me scroll back to aldehydes. Let me ask you this. In the carbon chain, this carbonyl group, where is it positioned? At the end. Yes, it is at the end. So there is no need to number it. Am I making sense? It's always at the end. Clear? But if you start looking at bigger ketones, this carbonyl group doesn't have to be it can be at the 3rd carbon, right? Or it can be at the 2nd carbon, hypothetically. Am I making sense? Everybody, good? So in the molecule that I am messing around with now, we number the carbons, and it's going to be 3 pentanone. The number 3 refers to the position of the carbonyl group. Does that make sense? But I can produce this molecule okay, and this is going to be 2 pentanone. Before I will continue, any questions on this? Because we can number these carbons the following way. Good? Clear? Everybody? Now, what about this 3-methylcyclohexanone? So, look at this. Imagine that we have this molecule, okay? How many carbons do I have in this formula? 6. And this is a cycle, and there are no double bonds, so it will be cyclohexane, right? Now I'm going to add carbonyl group. Okay? I still have 6 carbons, so I replace the E at the end with O-N-E. Am I making sense so far? Now we transition from this molecule to this. Carbonyl group, it has a priority in terms of the importance of numbering. So, where do you start numbering? Do you start numbering from chlorine or methyl group CH3, or you start numbering from the carbonyl group? The answer, and remember, there is no, it's not something chemically important. It's the agreement that a bunch of nerds achieved at some point in their lives, right? They agree that in a case like this, we start with the carbonyl group. It is more important. So we don't give the number 1, therefore we start numbering the carbons 1, 2, 3, 4, 5, 6, 3-methyl cyclohexanol. Am I making sense? Okay? So, since this group, the carbonyl group, is characterized by highly negative oxygen, it can form hydrogen bonds with slightly positively charged hydrogens of water. This is water molecule. Okay? Does that make sense? Which means that, and same story is true for ketones, slightly negative oxygen of carbonyl group can form hydrogen bonds with the slightly positive hydrogens of water. So, what it means is that aldehydes and ketones potentially can be dissolved in water. Am I making sense? Now, there are limits. Ketones and aldehydes are soluble in water if they have 4 or less carbons. Why? We talked about it last week on Wednesday when we discussed alcohols. The longer the chain, the more nonpolar impact, so to say, it has on the molecule. Essentially, in the aldehydes and ketones that have only 4 carbon, 1, 2, 3, or 4 carbons, the nonpolar part of the molecule, the carbons and hydrogens, is equilibrated by the polar part, the carbonyl group. But the more nonpolar carbons you start adding, the more nonpolar the molecule becomes. Okay, does that make sense? So, a few things that are, important, little important, but stuff that you can encounter in the household. So, acetone, or propanone here, it's a ketone, a very good solvent, organic solvent, paint diluent, Formaldehyde. So, formaldehyde is a gas. I can confirm that it has really a pungent odor, and the gas itself is very toxic. If you get exposed to formaldehyde, you can get sick. Okay? But there's a water solution of that gas called formalin. You probably have heard this term. So it's the water solution of formaldehyde, which is used to preserve biological specimens. Formalin kills everything. Like if there are any bacteria, viruses, whatever, it's going to kill everything. It's going to preserve the specimens for many, many years. They're not going to be rotting. Does that make sense to you? There's some more here. A lot of aldehydes, have specific aromas. Obviously, you don't need to memorize the which one is which, but you can see that almond smell, vanilla smell, and cinnamon smell are due to certain aldehydes and ketones. Making sense? Okay. So now let's classify these molecules as an aldehyde or a ketone. A ketone, because carbonyl group is not at the end. B aldehyde. C aldehyde. D ketone. Questions about this classification here?
Can you explain why B and C are aldehydes?
B and C? Yes. So take a look. So since it's recording, I'm going to repeat your question. So the question is why B and C are aldehydes. In an aldehyde, that carbonyl carbon okay? It is connected to what? It's connected to oxygen, right? It's carbonyl oxygen. I'm gonna name it. And check this out. A hydrogen and another carbon. Does that make sense? Now, if you look at this is the definition of an aldehyde. The carbonyl carbon forms one bond with a hydrogen, another bond with another carbon. So if you look at C, you see the same story. This carbon and this hydrogen both form bonds with a carbonyl carbon. Does that make sense? Now, on the contrary, if you look at, let's say, this cyclohexanone, this is the carbonyl carbon. And it forms bonds with two other carbons, which make it a ketone. Okay? So, let's talk a little bit about the reactions that these molecules can participate in. First of all, alcohols can be dehydrated. Okay? So imagine you have ethanol, this ethyl alcohol. So you mix it with some acid. Acid serves as the catalyst. It does not participate in the reaction. And you heat it, and this hydrogen and this OH group, which is characteristic. Remember, OH group is what makes an alcohol, right? They are released as water, and what you have now, you have an alkene. Okay? So form a double bond. Am I making sense? Okay? And I can't stress it enough. It should be adjacent hydrogen and adjacent OH group. Does that make sense to you? Now, we're going to talk about oxidation and reduction. And I'm going to go slow. I'm going to make statements, and I'm going to ask you whether or not those statements make sense. So what is oxidation? Oxidation increases the number of carbon-oxygen bonds. Does that make sense? And it can be achieved by two routes. One is adding more oxygen atoms to the molecule, or by losing hydrogen atoms. Good? Reduction, as you can imagine, has an opposite definition. So in case of reduction, you reduce the number of bonds between carbon and oxygen. So, let's take a look what we're talking about. Okay? So let's say we have a primary alcohol. We talked about it before. The primary versus tertiary versus secondary. I'm going to remind you briefly. Okay. Let's give ourselves some crash course, okay? So, primary alcohol. OH group, the carbon that's connected to OH group is connected to one other carbon. Does that make sense? Then we have secondary alcohols. So we have, for example, this. Make sense to you? So the carbon that's connected to OH group is connected to two other carbons. I think I know what to do. I'm going to reiterate it. And then we have tertiary alcohols. So the situation will look like this. Sounds good? Hold on, I'm not finished. I'm not finished. I'm going to illustrate so you remember what we're talking about. So, if a carbon atom is connected to OH group, we're going to give it yellow shade, okay? Does everybody agree with the shading? Right? Now, we have carbons connected to the carbon connected to OH group. We will give this pink shading. Reasonable? So if you look at primary alcohol, this is the carbon connected to the carbon connected to the OH group. How many pink carbons are there in the primary alcohol? One. If you look at secondary alcohol, these two carbons are connected to a carbon connected to OH group. How many of these pink carbons are there? Two. Secondary alcohol. How many pink carbons? 3 tertiary alcohol. Make sense? Better? More confident? Okay, let's go back to this illustration. So here's what happens. I have primary alcohol here. Okay? So in the left, in the primary alcohol, in ethanol on the left, How many carbon-oxygen bonds do you see? On the right, it's an aldehyde. How many carbon-oxygen bonds do you see? How many bonds between carbon and oxygen do you see? Come on.
It's a double.
It's so two, yes. So two carbon-oxygen bonds. By definition, if you increase the number of carbon-oxygen bonds, it's oxidation. Okay? That makes sense? So 2 is more than 1, therefore oxidation. Sounds good? Now, we just got aldehyde. This is what we got in the previous slide. Ethanol. Now, this molecule can be oxidized even further to carboxylic acid. We're going to talk about carboxylic acid eventually. Now, another term for ethanol is acetaldehyde. And another term for ethanoic acid is acetic acid, or vinegar. Does that make sense? All good? You follow? So, how many carbon-oxygen bonds are on the left? On the right? 3 is more than 2. Also oxidation. Does that make sense? So we can summarize it this way. Primary alcohols can be oxidized to aldehydes, which can be further oxidized to carboxylic acids. And from left to right, it is oxidation. Okay, so far so good. Any questions? Now what about secondary alcohols? So now that you are familiar with the whole concept of the secondary alcohols, okay, so secondary alcohols are oxidized to ketone. How many carbon-oxygen bonds do we have on the left? On the right? 2. So what you have on the left is 2 propanol, okay, or another term, isopropanol. On the right, you have propanone. Why don't I put any numbers in there? Why don't I say 2-propanone? Why just call it propanone and just, I don't need to put the number in? Anyone? Any ideas? If I will put carbonyl group at the end, will it be a ketone? No. It wouldn't be, right? So it cannot be 1-propanone. It's just only in the middle, and there's only 1 carbon in the middle. And that's why I don't need to number it, okay? The common name for this? Acetone. Okay. Tertiary alcohols don't oxidize because you cannot remove any hydrogens. Okay? Does that make sense? Okay? So we can't really reduce the number of carbon-hydrogen bonds or increase the number of carbon-oxygen bonds. So, right, so methanol poisoning. Have you ever heard of it? No? That's, yeah, completely different culture. So, it's a toxic compound, methyl alcohol, okay? Now, it is not found in windshield washer fluid anymore. Methanol has been removed from practically, okay, paint strippers, sure. There are some chemicals that are more aggressive, but windshield washer fluid, absolutely not. Okay? So this is the problem with methanol. If you, hypothetically, drink methanol, it is very quickly oxidized to formaldehyde. And it's highly poisonous. That makes sense? Formic acid isn't great either. By the way, on the unrelated note, are you familiar with fire ants? The burning sensation comes from the formic acid that they release during the bite. And the original, when formic acid was first obtained by scientists, it was obtained from ants. They literally put ants in a flask, heated it out. The acid evaporated, they condensed it, so it was pretty gruesome, but they got formic acid out of those fire ants. Okay? Does that make sense so far? Now, methanol is, I can tell you, in Russia, there are regular cases of methanol poisoning because people make counterfeit alcohol. Methanol is very cheap, and they just add methanol instead of ethanol, and people get poisoned. And if investigation happens, there was I would call it an outbreak. 40 or 50 people died of poisoning, hundreds got in a hospital. Methanol affects vision, so you may lose vision, you may become blind, completely blind, irreversibly blind, so it's pretty bad. So methanol is not used normally in household chemicals anymore. Ethanol, everybody knows what it is, right? Okay? It's a drug. It is a depressant. And this is the metabolism of ethanol. So it starts with ethanol, acetaldehyde. And then I must insert another step that authors of that book missed. There is an acetic acid here. Okay? So when a person consumes ethanol, first, liver metabolizes it into acetaldehyde, which is further metabolized in acetic acid, which eventually is metabolized to carbon dioxide and water. Am I making sense? Okay? Good? Now, the person who's an alcoholic, they drink more often and expose their liver to that poison more often. So, liver, quote-unquote, learns how to metabolize it faster. Does that make sense? But that's not the end of the story that I wanted to tell you, because I really like to put the link between chemical and the condition. So ethanol itself is a drug that is a depressant. Is it toxic? Sure, to some extent. Okay, makes sense? But acetaldehyde is actually quite toxic. So when people abuse alcohol, they drink too much, what do they experience in the morning? Hangover. This happens because their liver, at some point, cannot cope with the amount of alcohol that gets into the system. That makes sense? Liver is responsible to run the full gamut here, from ethanol to carbon dioxide pretty much, and it just can't keep up. So the amount of acetaldehyde increases in the blood. And that's just one part of a hangover. That's one part of the toxicity of alcohol. Does that make sense to everybody? And when people wake up in the morning, they feel shitty. This is why one of the recommendations is to stimulate your liver by something spicy. It kind of stimulates liver activity and helps it to metabolize the residual acetaldehyde, and you can feel better. Not so good idea is to, you probably have heard about hair of the dog. It works biochemically, it's just not a good idea. Okay? That makes sense. Now, another thing, so if you would look at the composition of hand sanitizers, they either include ethanol as the active compound, or isopropanol. Okay? So now imagine, and if this sounds very unrealistic for you, imagine someone will drink hand sanitizer. I grew up in a completely different culture. For me, it's not the question if, it's the question when and who. Okay? That's going to happen. So isopropanol, is that a primary or a secondary alcohol? Secondary. Secondary alcohols, what are they oxidized to? You can look at your notes. Ketones. Okay? This is acetone. So, if somebody decides to drink isopropyl rubbing alcohol, it will be oxidized by liver to an acetone. Is it safe? No. Is it as toxic as formaldehyde? Also no. This person will receive a massive bout of ketosis, ketoacidosis essentially. They will feel horrible, but they can be saved. There's time. In case of methanol, people can die in like a matter of 2-3 hours after consumption. So it's really dangerous. Okay? This is why, if you look at the composition of anything that contains alcohol, it's going to be either ethanol or isopropanol, because those are safer. Make sense? All right, moving on. Thiols. They can be oxidized as well, but in this case, they form, so the hydrogen atom is lost from the SH groups, and they form disulfide bond. One sulfur connects to another sulfur. Why this is important? There's an amino acid called cysteine, which contains an SH group. When these SH groups are oxidized, they form this bridge, disulfide bond, disulfide bridge between two cysteines. Okay? And I want to highlight this statement. It is a correct statement. So your hair contains protein called keratin. Do you follow my train of thought? And your hair, they have certain shape. They may be straight, they may be curly, that kind of stuff, right? The shape depends on the shape of the keratin within the hair. The shape of the keratin, in turn, depends on these disulfide bonds. Are you with me? So, what do you do? And I'm not the hair authority, as you can tell, but what do you do if you want to go from straight to curly or vice versa? You apply chemicals and heat. Does that make sense? You do it to break down those disulfide bonds, to essentially change the shape of that protein. When you do this, and you just like, you did whatever, like you straighten your hair or vice versa, what's going to happen to your hair eventually? Let's say you make it curly, eventually your hair will become straight, because those disulfide bonds that you broke eventually will reconnect. It just takes time. Does that make sense? Okay. I mean, yeah, I guess. Anyone under age of 21? Everybody knows the effects of alcohol on the body. I'm not going to comment on this particular statement, but I want to say that Russians are excluded. Okay, let me pause it. So aldehydes and ketones both contain the same functional group, carbonyl group, in different locations within the chain. So how can you distinguish them? So to distinguish them, scientists use the Thiols test. Okay? So Thiols reagent contains a positively charged silver. Okay? And this silver essentially oxidizes ethanol aldehyde into an acid. When silver oxidizes ethanol, silver gets reduced, and you have, it's a silver mirror reaction. When you run this reaction, the walls of the tube will be covered with a very, very, very thin layer of silver. It's super characteristic. It's a gorgeous reaction. Okay, does that make sense? Now, there is another reaction that we will explore at some point when we're going to test a variety of biological molecules in the lab. It's called the Benedict's test. We're also going to mention Benedict's test in the unit chapter 13 about carbohydrates, but Benedict's test essentially allows you to detect the aldehydes that have the OH group nearby. Let me illustrate. I know. Talk is cheap. Give me a second. Okay. So what we're talking about is this. Does that make sense to you? Benedict's test detects it. And I'm going to highlight this, right? So you have carbonyl group. Can you see that? And you have OH group next to it. That's what Benedict's test is for. Okay? So this is the reaction showing you the detection of hydroxypropanol. So I have these two aldehyde groups, the aldehyde group and the OH group next to each other. They interact with the copper in the Benedict's reagent, and that results in the formation of super noticeable, like very, very intensely red colored precipitate, okay, and the acid. If you will take a regular aldehyde, so instead of 2-hydroxypropanol, you will take just propanol, which is no reaction, because there is no adjacent OH group. Am I making sense so far? Okay. So why we are interested in Benedict's test? Our next chapter will be about carbohydrates. And some carbohydrates have this aldehyde group at the end with OH group adjacent to it. So what you're looking at on the left is the glucose. Okay? The glucose will turn the Benedict reagent, the blue one on the left, into the red precipitate. Okay? So there are other sugars that do not have an aldehyde group at the end. Am I making sense? They will not produce that reaction. If you will put carbonyl group somewhere in the middle, there will be no reaction. Okay. Now, just like you can oxidize aldehydes to carboxylic acid, you can reduce an aldehyde or a ketone. So you can use some kind of a strong reductant, borohydrate, or just bubble oxygen through. Now, what is the reduction? We talked about it. The number of carbon-oxygen bonds is reduced. Okay? And usually you need some kind of a catalyst, such as nickel, palladium, platinum. So this is an example of the reduction of aldehydes and ketones. Now, I want to remind you, folks, remember we were talking about the oxidation of alcohols, how primary alcohol, like ethanol, is oxidized to acetaldehyde. Remember that? That reaction? This reaction. So primary ethanol is oxidized to ethanal, aldehyde. And if we scroll farther back, secondary alcohol is oxidized to a ketone. Make sense? You can run this reaction in reverse, making it the reduction. And if you take propanol or propionaldehyde, this group will be reduced to this. You go from aldehyde to alcohol. And when you go from propanol, propionaldehyde, you get a primary alcohol. If you will take propanone, which is a ketone, okay, by reducing it, you convert this carbonyl group into the OH group, and you get a secondary alcohol. So remember that those two reactions can go back and forth. You can take primary alcohol and oxidize it to aldehyde, or you can take aldehyde and reduce it to primary alcohol. Okay? So, what do you think is going to be the product of this reaction? The oxidation of a, first of all, let's start with this. Primary or secondary alcohol here? This one. Primary or secondary? Secondary, because this carbon is connected to two more carbons. So when you oxidize the secondary alcohol, what you're going to get? Okay? So if you take what will be the product of the reaction B when you oxidize this molecule? Okay, primary or secondary, or, well, primary or secondary alcohol? Primary alcohols are oxidized to what? Aldehyde. So, and aldehydes are oxidized to carboxylic acids. Okay? Does that make sense?
So what's the you said for the secondary alcohols, the carbon has to be linked to two more carbons, right?
Say it one more time.
For secondary alcohol, the carbon has to be connected to two more carbons.
Yes.
And then for primary, what is it?
Just one. So here, look at this. This carbon is connected to one more, and that's it. Hold on. In this example, this carbon is connected to one and another. Two more. Secondary, right? So, essentially, this hydroxyl group will be first oxidized to carbonyl and then to carboxylic. Okay. Questions? Carboxylic acid? No, that's a terminal one. You cannot oxidize, do anything about carboxylic acid without breaking the actual chain of carbons. I mean, you can oxidize it, but it's going to be into carbon dioxide and water. So there's, like, that's it. If you want to keep the entire chain, that's it. Okay?
You can't oxidize tertiary.
Not without breaking carbon chains. Not without breaking carbon chains.